Hi, I'm Melanie.
And I'm Tiger.
And I'm Matthew.
And in this video, we'd like to present our work on facial expression recognition using convolutional neural networks. First, let's start off about what is the facial expression recognition problem and why we want to study it. Think about your daily lives. You probably spend a significant amount of time interacting and communicating with computer systems. In fact, you're probably doing so right now. In the beginning, only experts could really interact with computer systems, usually using terminals, such as shown on the left. As we move forward into today's society, almost everyone is able to interact with computers due to complex user interface systems. For example, phones, touchscreens, tablets, and computers. And finally, looking forward toward the future, things seem to be moving toward a time where you're able to communicate with computer systems in a similar way you would just with another human, by talking to them. However, as we move toward this future, there's a large problem. Is that up to 55% of effective communication is nonverbal. This means that if computers are only able to look at audio, they may not be able to fully understand humans interacting with them. So what can we do about this? Well, a potential solution is to create algorithms that enable computers to recognize facial expressions. There are a number of different ways this can be done, but convolutional networks have historically excelled at these tasks. However, this brings us to another very large problem, that the computer algorithms may be biased toward either race or another minority feature. For example, since we can't really understand what the algorithms are seeing, they may incorrectly identify that an African American person is angry more often than other races. So now that we know the motivation for studying the facial expression recognition problem, let's look at the specific questions that we decided to answer. So first, how does a simple CNN compare to a residual CNN in terms of accuracy for facial expression recognition? These are two CNN architectures which will be discussed in more detail later. And next, are there any racial biases among the algorithm predictions? So next, let's look at how we went about answering these research questions. The plan was to train two different CNN algorithms to recognize 7 different facial emotions. As mentioned previously, this was a simple CNN and a residual network. Both of these models are based on previous work in the facial expression recognition area. We would compare the accuracy of the models and then identify bias present in the models. In order to train and test our models, we decided to use the FER2013 dataset. This consists of over 35,000 labeled images of the 7 different emotions. This is one of the most popular datasets used for facial expression recognition. Next, once we trained the models, we decided to test them on the MSFDE dataset in order to identify possible bias. This dataset consists of 48 images for 5 different ethnicity groups.
For our first model, we constructed a simple CNN with 3 convolution layers. The input is a 48 by 48 grayscale image represented as an array of pixels. The first convolution layer is followed by an average pooling layer, while the next 2 are followed by max pooling layers. The result from the convolution layers is then passed through 2 fully connected layers. The final output is passed through the softmax activation function, resulting in a probability prediction for each of the 7 emotions. Out of the parameter variations we tested for this model, we found that the model achieving the highest validation accuracy had 3 convolution layers, 64 filters for each of those layers, and 512 and 256 units for the first and second dense layers respectively. This is the final architecture for the simple CNN, which we use to evaluate the test set for the FER2013 dataset, as well as the MSFDE dataset. When evaluated on the FER2013 test dataset, the simple CNN model achieves an accuracy of 56.5%. Here we see the confusion matrix for the predictions of the model. The most accurately predicted expressions are happy and sad, with accuracies of 84% and 62%. For the other emotions, angry gets an accuracy of 43%, fear 38%, surprise 43%, and neutral 57%. One notable result is that the simple CNN did not predict disgust for any of the images, even though there were 55 images in the test set that were labeled as disgust. This is mostly due to an insufficient amount of training data, which was highly imbalanced. Only 1.5% of the training samples were for the disgust emotion, while 25% of the training data was for happy. These results of the simple CNN demonstrate that it's difficult to predict complex facial expressions using a simple architecture, especially expressions with subtle differences such as anger, fear, disgust, and surprise. In addition, we see that an unbalanced training dataset can have significant impact on the bias of the model.
For our other model, we constructed a residual network based off the standard ResNet 18 model with modifications proposed by the paper Facial Sentiment Classification based on ResNet 18 model by Zhou et al. This included replacing the average pooling layer with a global average pooling layer followed by 2 convolutional layers. Similar to our simple CNN, the input is a 44 by 44 grayscale image and output is a relative confidence score for each of the 7 emotions. By exploring different training parameters, we found that the model achieving the highest validation accuracy had used a batch size of 64, a learning rate of 0.01, and a momentum of 0.95. The model trained with these parameters was evaluated on the test set for FER2013, as well as the entire MSFDE dataset alongside the simple CNN. The residual network achieved an accuracy of 61.5% on FER2013 and predicted all expressions with fairly reasonable accuracy. We can see that happy, disgust, and neutral were predicted more accurately at 72% to 78%, while surprise, fear, sadness, and anger were predicted less accurately at 47% to 52%. We can attribute the group of expressions which are predicted with a lower accuracy to the observation that they resemble one another more closely, introducing some natural ambiguity and making them difficult to distinguish. This can be seen by the model's most frequent mistakes being labeling anger, fear, and sadness as surprise, as well as labeling surprise as fear and sadness.
Now we're going to demonstrate the simple CNN on a few examples. First, we're going to load the test data in the simple CNN with the parameters that achieve the highest accuracy. Then we'll call the predict function, and we compare the predicted emotions with the actual labels. So here in this graph, we have the actual labels in blue and the predicted labels in orange. The simple CNN model overpredicts for happy and neutral and underpredicts for the other emotions. In particular, we see that the model doesn't predict disgust at all. Now we're going to take a closer look at some image examples. So for the first image here, the model correctly predicts it as happy. In this case, the model is very confident in its prediction, outputting a probability of 99.9%. For this next example, both the true and predicted labels are sad. Looking at the prediction probabilities, the model is fairly confident that it's sad, since it has a probability of 86%, while the second highest probability is fear, which is at 9%. And for the third image, the actual emotion is disgust, but the model thinks it's angry. It outputs this prediction with 79% confidence, and the model only has a confidence of 3% for disgust. And this is one example showing that the model isn't very good at differentiating between nuanced expressions. The simple CNN fails to predict disgust for any of the images and instead confuses disgust expressions with anger, fear, or sad.
Now let's take a look at a demo of our ResNet model. First, we'll load the model from file, and then we'll use our model to predict labels for our test dataset. Now we'll compare the distribution of our predicted labels with the true labels. We can see here that we overpredict for happy and we underpredict for fear and anger, for example. However, the distributions are fairly similar and have a very similar shape. Now let's look at some specific examples of cases from the test dataset and see how our model behaves. First, we can see here that in this example with the true label happy, our model also predicts happy and does so with a very high confidence. Next, if we look at this example, we can see that the true label is neutral and our model predicts happy. Although our model is incorrect, it predicts neutral, the true label, with the second highest confidence. In this example, with the true label of surprise, our model predicts fear. Our confidence goes as follows. Our model is most confident in fear, then next up is sadness, and then it's third most confident in surprise. You can see that with these two examples, there could be some ambiguity based on the image, and even a human might predict a different label than was actually given in the dataset. So there could be some ambiguity, and we can see that that might be one contributing factor to why the model struggles. Finally, let's look at this example of disgust. In this example, our model predicts disgust with a fairly high confidence and predicts it correctly, whereas the simple CNN was unable to do so.
The residual network achieved a higher accuracy on the test set than the simple CNN, which is in line with our expectations. An interesting result is that the residual network has a higher accuracy for anger, disgust, fear, surprise, and neutral, while the simple CNN has a higher accuracy for happy and sad. This indicates that the residual network is better at determining differences between more nuanced facial expressions. Another important difference is that the residual network can classify images as disgust. This higher accuracy of the residual network agrees with our hypothesis, as the residual network can extract a greater number of useful features due to having residual blocks and more convolutional layers. On the other hand, the simple CNN seems to be more effective at predicting facial expressions that have more distinct characteristics, such as happy and sad. This result was more surprising, and it shows that sometimes a simpler model is sufficient for differentiating between classes if they are distinct enough, and it's not necessary or even harmful to introduce more complex architectures.
Both models were run on the MSFDE dataset to compare how the distribution of predicted facial expressions varied for different races. Using a chi-squared test, it was found that both models produce statistically significant results, which indicate that the distributions of expressions they generate would be different for different races. This was despite generating similar average prediction accuracies between the different races for both models. Ultimately, the takeaway is that using neural networks to predict facial expressions can potentially produce ethnically biased results, which can be hard to spot. If one of these models were to be used in a way that impacts the lives of people, extreme caution and care should be put in to make sure that one's ethnic background or other attributes of their physical appearance do not confer a significant advantage or disadvantage in the system. If one of these models were to be used in a way that impacts the lives of people, extreme caution and care should be put in to make sure that one's ethnic background or other attributes of their physical appearance do not confer a significant advantage or disadvantage in the system. That being said, one of the limitations we faced was in the scarcity of racially labeled facial expression data. The MSFDE is a fairly small dataset with only 580 rows and 4 different races labeled. So, it would benefit future analyses to have a greater volume of data and more categories, for example having more ethnic granularity or labeling other physical attributes as well. Thanks for watching! Please let us know if you have any questions on GitHub.